Meeting is being recorded. All right. Is it recording? Shall I start? Perfect. Okay, perfect. Thank you. Good morning, everybody. So today we'll start discussing about explainability in neural networks. Now, this is actually a mammoth of a topic, mainly because of essentially we'll go through today. Every year, there's like hundreds of different papers that come out on this particular topic, which is how do we explain or how do we understand or interpret what neural networks are. The reason for that is we'll actually go through it today because it's not easy. The new GPT basically has 500 trillion parameters. How is it possible for us to actually go through and try to understand what a neural network is doing or how the decision-making process is going to occur? So again, every year, hundreds of papers that come through, but we'll be discussing some landmarks or most important kind of concepts that are important for explainability. So as Professor Gassan mentioned, there'll be three different subtopics within this like big chapter on explainability. The first one is about just the convolutional neural networks itself. I think every one of us has access or knows what convolutional neural networks are. That also every one of us also has had trouble basically trying to troubleshoot it, debug it, or even to get it to work. So one way of trying to debug or troubleshoot is to essentially try to see what it is giving us, to try to interpret what is going on within the neural network. And the goal of today will be to try to go through to understand these convolutional neural networks. The next two things, which is the type of explanations and evaluations of explanation, is something that we'll look at on Monday. So let's start with a very simple question. What is explainability? Now, this, again, as I mentioned, it's a mammoth of a topic. So it's very difficult to just say in one sentence what explanation is. And this is a very concise and I would say a very gross kind of a way of trying to say what explainability is. So it's the ability of an entity to explain or justify its decisions or predictions, essentially. So if this entity, for instance, is a neural network, then what we have is explaining neural network. So we have a neural network, we have an input image, it passes through it, and we get certain kind of a decision. Explainability asks us that the neural network should be able to explain its decisions. And it needs to explain the decisions to human beings. And that is what is sometimes very difficult, because it's not just a very competent engineer, let's say, who needs to be able to understand a neural network. It's also a regular human being. Anybody who's using this kind of a neural network or an AI technology that uses a neural network must be able to understand it. And this is where the difficulty comes in. It has to be able to, convince a child or an expert or any of these users, essentially, of these neural networks. Now, why does it matter? Well, it's pretty straightforward. We need some kind of trust within neural networks, within an AI system that uses neural networks. Hence, it's very important that we understand how it works. And this is where explainability comes into picture. Like, think of these scenarios and medical scenarios where we're using neural networks to help us kind of interpret what is going on. We don't want a neural network to just spit out a decision saying that surgery or no surgery. We want it to explain itself. We want a good reason as to why a surgery is required or not required. Same thing in something like autonomous systems, like let's say autonomous vehicles. It's making certain kind of decisions. Let's say there is a some kind of moral quandary it's facing. It has to either stop the car or keep on moving. It makes a decision, a split-second decision, but afterwards it needs to be able to explain itself as to why this particular decision is made. So for us to actually get this kind of trust within neural networks, it has to be transparent. It has to be able to say why it's doing what it did. And that is why explainability matters. So till now, we have only considered neural networks to be these kind of black box models with a very large set of parameters, doing some kind of matrix multiplication, Bayes addition, some kind of calculations, and it's able to spit out a certain number, which we can then use to make decisions. But today, we'll be looking at what these matrix multiplications actually are, and if we are able to visualize it and try to understand it. So this will be the setup, basically. At least until this point, this is the setup we have used. Some kind of a deep model and some data that is passed into the deep model to get an output. So if you're thinking about ImageNet dataset, which is probably the most common dataset there is for any kind of image recognition, an input image, which is of size 224 cross 224 with 3 channels, which is R, G, and B, is passed through this deep model, and we get an output of length 1000. This vector has 1000 numbers, where each of these numbers is essentially showing us, okay, what is the probability that this logit belongs to this particular class. Now, this based on whichever the maximum output is, we say, okay, this is the decision, this is the class that this image is going to belong to. So that is all what we know about a neural network till now, and this is insufficient for explaining why this decision is made. So one way that we'll be looking at today for how to do explainability is to say, okay, what are each of these layers doing? Like, let's say this particular network here has about 5 convolution layers and 2 fully connected layers. What exactly is each of these layers doing in order to get us that final output? It goes from a dimensionality of 224 cross 224 cross 3 into a dimensionality of 1000 cross 1. So we want to know what exactly is happening within these layers in order to get us to that particular stage. So let's start by simple things. The most simple thing, which is just visualizing your filters. And this is the first level of interpretability or explainability. I'm going to take the first convolution layer filters. There's going to be like, I don't know, AlexNet, for instance, has 11 cross 11 cross 3 as the filters, and there's 64 of these filters. So each of the things that you see here on the top left image is 3 cross 11 cross 11 and 64 of them. So there's 8 on the rows and 8 on the columns. There's 64 of these filters, and each of them is 7 by 7 pixels with 3 channels, which is RGB. The color comes because of 3 channels, and the square structure because of 7 cross 7. And this is what it looks like. It's a bunch of lines, bunch of edges at different angles that are going through together. Now think about what a neural network does. This layer, all these filters, they convolve against your image. In other words, each of this, let's take this one filter, for instance, or maybe this filter. Hopefully you can see where my mouse is pointing to. And this particular filter is this kind of a vertical edge. What it does is it convolves across the image. Once it convolves across the image, it will basically highlight where the edges, the vertical edges are going to be, because that is where it kind of overlaps. And when you convolve something, hopefully you remember from convolution that you did in previous courses, it's going to activate that part of the image where this vertical lines are going to be, and you get this kind of an edge detection kind of a thing. So that is essentially what is happening in your first layer. And remarkably, this is essentially how the human visual system also works. In the V1 cortex, essentially, this is how we go through and try to find some kind of patterns within the image. So the first layer goes through and finds these kind of low-level edges, colors, textures, and backgrounds throughout the image in order to find something. So, and we know this because we are able to visualize it and see what these matrices look like. So you can do that yourself as well. Like go through your, I'm sure in the project you're working on these things, see what the first layer is looking at. Ideally, it needs to be looking at these kind of simple things, which is the edges and colors, textures, backgrounds. If not, then you have not trained your neural network as well as you could have. And in that case, you would have to, change your kind of, I don't know, maybe a learning rate, or maybe something like the L2 regularization or something like that, in order to make sure that your first layer is looking at these kind of features. So let's say that so these basically filters in the first convolution layer. So across different architectures, this is what is done. So this is why I was mentioning, like, you can go through any data that you're using, any network that you're using. Ideally, you want to be able to see these kind of things. Of course, if you're not working on RGB images, you won't get these kind of color filters, but essentially you'll still get these black and white images of these simple concepts. So on the left-hand side is AlexNet, on the right-hand side here is ResNet, and you can see that the first layer of filters essentially learns very similar looking concepts, which are these edges and colors kind of simple concepts. Any questions on what we are trying to do here in the first layer on trying to just visualize it? Perfect. All right. So let's go to the next one. Now, we just discussed about, okay, what happens in the first layer. It's very easy for us to understand what happens in the first layer because the convolution happens on the image itself. So whatever concepts are in the image will be reflected back to us within the first layer. But as soon as you move away from the first layer, you start getting basically a combination of these edges. And spatially, they don't mean much to us. We don't understand what they mean. So here we have this kind of which layer, convolution layer 2 weights. So convolution layer 1 weights, you have these edges, looks beautiful, everything looks good, we can understand it. But let's go to the next layer. We have 20 cross 16 cross 7 cross 7 as our actual weights that are working on top of the first layer. It's and I know these are very small. You can actually look through it and you can try to see what they are. It's very difficult. It's almost impossible because anything in the higher layers, they're not interpretable to us. Because think about what is happening here. It's convolving across the activations of the first layer. And because of that, it's just basically weighing which edge is more important. So it's not spatially identifiable as it was in the first layer, and we won't understand it. Essentially, the goal of this is to, this slide is to say that what worked in the first layer is not going to work later on. And this is going to be a common theme throughout. So whatever works in the, let's say, the middle layer is not going to work in the first layer. Whatever works in the first layer is not going to work in the last layer. And that's why this idea of explainability within neural networks is very difficult, and also, again, makes it very important as well. So what we usually do for looking at the intermediate layers, so let's say anything from the second layer onwards until the last layer, is one idea is to actually visualize the activations. So previously we were visualizing the weights. Now we're visualizing the activations or the outputs that you get from the weights. So this essentially is in conv layer 5. We have this, we're just showing in the AlexNet the activations of layer 5 of your convolution layer system. So in this case, when there is a kind of a maximally activated pixel, let's say at this particular point, we can say that this activation here is essential or helps us in understanding what exists within the image. Now, this is the idea. I'll go through the exact method on how we do it, but essentially we are trying to associate activations back to images. Before we were trying to connect the weights to images. Now within the intermediate layers, we are trying to connect activations to images, because that kind of a representation of your images. So how do we do it? Well, we use something called maximally activating patches, or visualizing maximally activating patches. So in this case, again, we take the convolution fifth convolution layer of this neural network, and we try to find the image patch that is maximally activated within this convolution layer 5. And by maximal activation, I mean I'm looking at that number within your activations in layer 5, which is the highest. So you're just choosing the highest point or number and seeing what this corresponds to within the image. So essentially how that is going to happen is you take this, this is essentially the methodology that we are going to use. So we take some kind of activations in a layer, and we have chosen convolution 5 for this example, and we pick one of these channels. We say, okay, there are 128 channels of 13 cross 13. That essentially means there are 169 numbers and 128 of these vectors of 169. I'm going to choose one of them. Let's say the 17th out of the 128 channel, and I'm going to pass through an image through, let's say I'm going to pass through these 4 images through my network, and I'm going to record the maximal activation and visualize the image patches that correspond to maximal activation. Hopefully that makes sense. So in this case, we are taking image patches in the input that cause the maximum activations of certain filters. We are taking an image, dividing into different patches, passing it through a neural network, and seeing that for this particular channel, this particular activation, which is the image patch that has the maximum amount of number. And in this case, you'll see 1, 1, 0.9, 0.9, and so on. So essentially, there's going to be some pixel in your very high dimensional space, which is only going to be looking at these kind of faces here, right? So if this is the patch that we are looking at, then there is going to be an activation that is going to maximize this particular patch. And it's going to show us that, okay, this is, if a patch exists, then this activation is going to be very high. That is essentially what this maximally activation patches is going to show us. Any questions on how this is done exactly? All right, we can move on. So we talked about 2 things till now, which is seeing what the first layer, or trying to understand, visualize, or interpret the first layer. And we looked at the middle layers. Now, this is again a gross approximation, but we are thinking that if there are about like 30 layers in a neural network, we are dividing into 3 phases. The first phase is the first layer. Second phase is anything between the first and the last layer. So again, a 30-layer neural network, there's 28 layers in between are going to be using this kind of maximally activating patches in order to try to understand what is happening within the neural networks. We are analyzing the activations within these neural networks. But the last layer itself, there's a different way of looking at it. The reason being that think about the dimensionality of what we went through. In the beginning, we started off with 224 cross 224 and cross 3, of course, the channels. But and then from there, we went to this very high dimensional space, 128 cross, I forget how much that is. I think it's like the total vector is going to be probably like something like 100,000 points. So 224 cross 224 has been taken down to 100,000. And at the end of the day, we wanted to come down to just 1,000, right? Because that is the number of classes we have. That is the number of logics that we want to analyze. So in that case, because of this dimensionality issue, now we are left with a smaller dimensional space. Now the neural network has to take these images and has to give certain output out of it. Hence, it's the most like class dependent, or similar classes are going to be very close to each other if you just take a distance. And that is why that's the kind of motivation basically we are looking for in order to do this last thing, which is the visualizing the last layer activations. So essentially, the idea here is that as you go through a network, you lose out on the unimportant information and you only have access to this class specific information. And you get that by exploring the last layer activations. So let's set up a few things. By last layer, I mean this final fully connected layer that is there at the very end. So in this figure in AlexNet, the last layer has 4096 cross 1000. That is the dimensionality of the matrix that we are looking at. Now, representations of entire input images instead of specific patches. Before this, we were discussing about, okay, I'm going to take patches, pass it through a neural network, and see what the activations were, or I'm going to take the weights and visualizing it. Now I'm just going to take the entire image and pass it through the neural network for this one, for at least understanding how the last layer works. And the idea or motivation is that similar embeddings correspond to same classes of input images. Again, a neural network has done its work. It has gone through the network. It has taken out the unimportant information. And the only thing that is left is these kind of class specific information that is now present within these embeddings. So when we have access to that, basically we say that that we are able to visualize these the embedding space and see what it is going to look like. So for this case, for instance, again, this is what we set up till now. We have 2 ways of doing this. So feed forward images through the network, and we can collect the final layer feature vectors, and we visualize input images that have similar last layer embeddings. So, you basically look at what the 4096 cross 1 vectors are going to look like and basically say that, okay, image A and image B have very similar looking 4096 vector. Hence, they are similar to each other. So these are essentially the results from here. So let's say we have, let's take this image, test image as this one image here, this purple flower that we are using. We pass this through the network and we get an output that is 4096 cross 1. We keep that 4096 cross 1 as a feature of this image. Now we can take, let's say there are 100 other images within your data set. I'm going to pass all the 100 images and I'm going to find the 5 or how much is it? 6 images that are closest to my feature vector of my test image here. And what you generally notice is that closest are these purple flowers as well. The similar class or the same class images are the ones which have the similar or the exact or very similar embeddings within the representation space. Now I can do that for any kind of a test image. If I take an elephant, for instance, and pass it through the neural network, I get a vector, I compare it against all existing vectors, and the closest ones are essentially these kind of elephants as well. Usually the research in this is basically how I define by closest. We can take the L2 nearest neighbor distance, but in most cases, you'll find many papers that go through and find other kinds of better distance measures, not just L2. But essentially, we want to find similarity or similar vectors in order to extract these embeddings in order to get these kind of or to query these kind of similar looking images. And this basically is explainability in the last layer, or we are trying to understand it by seeing what is the closest in the image. Now, one thing you will notice is the difference within the representation space versus input space. Now, if I take this dog here, bottom left corner, and I subtract it, or I take L2 distance against the dog in the image space itself, there's going to be a very large difference between the two because they're looking at different opposite directions. So, and that basically means that by just doing L2 distance in the image space, we won't be able to extract these two things, but they are the same. They are the same dog. It doesn't matter which orientation they're looking at, they're the same dog. And what we notice is that when we go through a neural network and we extract this distance out and we get these embeddings, they are very similar to each other. Neural network does not care about which side your dog is looking at, as long as it's a dog. And that for it is the most important part in the embedding. So that's why in the last layer, these two images are very close together, even though in the input space, they may not actually be close to each other. So this is one way of trying to interpret or understand the last layer of a neural network. Any questions for this method? So there's another way of understanding or interpreting the last layer, and that is dimensionality reduction. As I mentioned before, we have 4096 dimensions. This vector is 4096 cross 1. And if we want to actually visualize it like we did with the first layer and intermediate layers, it's impossible. We cannot do that. Reason being that this is such a high dimensional space, and anything about 3 dimensions, we will not be able to visualize. So there are a number of these kind of dimensionality reduction techniques that take this 4096 dimension vectors and reduces it down to like just a 2 cross 1, like a 2-dimensional array. And once you have a 2-dimensional array, you can go through and find, you can just plot it and see what it looks like. One of the most famous ones is TSNE, which is T-distributed stochastic neighbor embedding. We'll not go through how to do this. It's a little bit of complicated setup, optimization setup in order to get this method. But if you're using some kind of a library on Python, most of this is already implemented. So you should be able to actually go through and just call it as a function and should be able to get this kind of a visualization. What it does is it takes your images, or it takes the 4096 images and kind of puts it into a lower 2-dimensional embedding. Now, it's difficult to do this for 1,000 classes. So we're just showing here for MNIST dataset. MNIST dataset has only 10 classes. So ideally, what we saw before was that similar classes are grouped together, right? And you see that in the visualization as well. This green here is just one class. All of these images are close together. The purple is another class. Of all the images of that class are close together, same thing. And you'll be able to notice this kind of high dimensional data that is clustered together. And this is what you want to see. Again, the goal of all of this is for you to know if the neural network is working or not. And by showing TSNE, you'll be able to show that, yes, my neural network is working. Because sometimes accuracy by itself is very misleading. There can be a lot of biases for why your neural network is working. But in order to go past that, we need these kind of explainability and interpretability techniques. And that is where TSNE is probably one of the best and most common ones, where it's very straightforward to see this, right? You'll be able to 10 classes, there are 10 embeddings or 10 clusters. That means that a neural network has taken my images and put it into a representation space where everything is easily separable into these 10 classes. That basically is what TSNE is doing and what all these dimensionality reduction techniques can accomplish. I think this is like, we are done with like 1/3 of today's lecture. What we looked at till now was visualizing the network itself. So we started by visualizing the filters. We decided that the first layer filters are very interpretable. If we look at it, we can understand if a neural network is working. So if you want to see if your neural network is working, visualize the first layer. If it's not these kind of edges and vision concepts, then at least on natural images, this is basically what you need to see, or these kind of things is what you need to see. And once that is there, then well and good. But we can't do it in the later layers. So what we would have to do is do maximally activating patches. We need to take out small patches of a neural network, pass it through, and whichever layer you're interested in, an intermediate one, see the maximally activating patch, or in other words, the highest number within these activations, and see that, okay, this patch gives me the highest number in this image. So, this activation is good or important for this particular patch. So you'll be like something like faces, or I don't know what this is, but essentially all these kind of different patches will be activated based on them. Now, when you go to the final layer, there's two ways you can do it. The simplest one is the last layer embeddings. You can take your final 4096 cross vector, how much of a vector it is, and put it down into like 2 or 3 dimensions, something that you can actually see or visualize. You can use Python libraries. Disney is a very good method that does these kind of last layer embeddings, and you can visualize it. Nearest neighbors is another one where you can take any input test image and see what the closest images to them are. So one way of thinking about it is train versus test. So you have access to test images, you pass it through, you get a certain vector. Now compare this against all existing train images and say that, okay, these are the 10 nearest images to my test image. And since they're all of the same class, my neural network is doing well. Again, all of these are accessories to your accuracy. You already have accuracy. If it's high, it usually is not sufficient to either write a paper or to analyze a method. And if you're getting, let's say, 50 or 60%, it's good to do these kind of visualizations and see, okay, this is how I can improve my result. Maybe my first layer isn't working. Maybe my intermediate layers are not working. Maybe my final fully connected layer is not working. So this is a way of trying to debug your neural network that is not code-based. So this is about the network itself. Uh, Next, we'll go through something called saliency and occlusion, but that's a kind of a different topic. So before that, any questions in these three modalities of explainability? Yes. Um, so let's say you're working with something like natural images, which is basically any photograph that you can take of the real world. In that case, the first layer is always going to give us these kind of weights. It's always going to give us some kind of textures, some kind of colors, some kind of edges. So if your neural network is not giving you these kind of edges, then there is something wrong with the way you have trained your neural networks. So I would say the first check mark that you need to do when working with natural images is looking at these kind of filters. Once you finish that and it's working well, then you can move on to maximally activating patches to see if something is working or not. Again, this is a way of debugging if your neural network is working or not. Now, if you're working with something like biomedical data or seismic images or something else, you might not see these exact ways of visualizing the weights. It'll be something different. Usually, at least biomedical images, you'll have, first off, it's going to be white and black, and you'll probably just be seeing edges. That's it. Like if you have like 64 of these weights, all of them are going to be edges in different directions. So that is the difference between the two things. But your first check should always be to visualize these filters. Next has to be to actually, in my opinion, the first has to be this. The next one has to be the last layer because it's simpler. This is one layer. This is also one layer. Middle, you can have like 28, 30 layers. It's very hard to debug these kind of things. So start with the first layer, do the last layer. If those are working, you're good. You don't need to try to do the maximally activating patches. If nothing is working here, then you would have to go through the next stage, which is the maximally activating patches. Is that clear? Yes. If you're doing transfer learning, let's say, it depends on which one. Let's say you're doing from natural images to something like biomedical images. In that case, you start off with these kind of images, but it's going to change and it needs to change in order to do biomedical images. So the first check mark is that it is changing, that it has to change in a certain way. So you need to see that in the first epoch, it is something like this, while after 100 epochs, it is going to change to something else. The fact that it changes is the debugging tool in that particular case. And usually in transfer learning, you won't get these kind of beautiful looking concepts. It's since it's trying to forget what it has originally learned, and then it's trying to adapt to something new. It won't be as good looking as these kind of edges and orientations and stuff like that. So in that case, I would suggest doing the last layer embeddings and transfer learning at least to see if how good it is working there. Yes. Mhm. Oh, yeah. So this essentially, the way we get this is there's a lot of kernel embedding stuff that is involved. So there's a lot of optimization and kernel embedding stuff. There are a number of different ways of trying to go from 4096 in order to go to down to 2 dimensions. The fact that when we have to visualize it, we are always constrained just because the way human beings work. We are constrained with 2 or 3 different dimensions. That's it. But let's say you want to increase it to 10, you want to take a kernel and put it up to 10 dimensions. What you would do is you can take the 10 dimensions, take 2 dimensions within the 10, and then have like 10 different images, 10 different of these embeddings where you'll have, let's say, dimension 1, dimension 2, then you'll have dimension 3, dimension 4, dimension 5, dimension 6, or like a combination of all those things. And you can see those things as well. Basically, you're trying to find a correlation between all these dimensions. And if those correlations are essentially clustered by themselves. So you can do it, of course. You can take any kernel embedding trick in order to find what the visualization technique or to visualize how these are.
For higher dimensions, when we are like constraint casing or any dimensional reduction technique, it's going to be non-trivial. So yes, there might be a situation wherein our model is correct, but then the TSNE is not accurate. So in that case, how would we debug like the TSNE? Is there any way?
Absolutely. That is definitely a problem. And the only way I can think of is by having multiple different methods, not just testing. You'll have UMAP is another very famous technique that you can use. PCA is probably a pretty old, but there's like isomaps and these other kinds of dimensionality techniques, reduction techniques that you can use as well. So it's like, getting doctor's opinion. Yes, one may not be accurate, but there's no way of us knowing what is accurate. So you just do it as many times with different people as possible. So in this case, you would have to go through different experts and see what their diagnosis is. So in this case, that would be different methods of doing it. But you're absolutely right. There's no one way or one method that is always going to give us a good representation. Even if your neural network is working well, maybe it's the TSNE that is the issue. So it's not like if this is working, then your neural network is working. But if this is not working, does not mean that your neural network is not working. So that kind of a bijective relationship does not exist in these methods. Yeah. All right. So there's no questions. We can move on to the next one, which is saliency-based methods. So the question we're going to be asking is which pixels matter, saliency via occlusion. Now, the title itself is, I would say, very heavy. There's a lot of words here. So let's start with which pixels matter. Hopefully this part is straightforward. We have an image. Till now, we have been looking at, okay, what is the embedding? What is the neural network weights looking at? What is the activations looking at? Now we'll directly be looking at the images themselves and saying that these are the important pixels, why this image was classified this way, or these are the important pixels, why such and such a decision is made. Next one, the next parts of this title is saliency via occlusion. Saliency is basically this idea that certain pixels are more important than others. For what is basically based on what the decision-making system is, which in this case, neural network. What does a neural network value within an image in order to make a certain decision is essentially what we are looking at. Occlusion is basically this idea that I'm going to take this kind of a patch, this gray patch, I'm going to put that on top of an image. So let's say this elephant exists. I'm going to take a gray patch and I'm going to put it on this image. Now I'm going to pass it through. So I'm occluding the image in order to check how good a neural network is at kind of ignoring the patch and making a decision based on the remaining part of the image. Because it doesn't matter, right? If I look at this image, it doesn't matter if the gray patch exists here or not. I know that it's an elephant. Why? Because I can see the face, I can see the ears, the tusk, everything. It's still all gloriously visible. So I can still say with 95% confidence, or at least a neural network will say with 95% confidence that this picture belongs to that of an elephant. So one thing I think I need to mention here is don't make this zero. Like if you are trying, if you are going through and trying to use this to understand a network, don't make the patch zero. Make the patch because when you do subtraction, like mean normalization, this is zero patch essentially becomes something negative. So it adds to the network. So it's a bad intervention. So what intervention you need to do is put this kind of a gray box, essentially, like 128, 128, 128. Now, let's say I take this gray patch and put it on the face of an elephant. Still, for us as humans, it's pretty straightforward to see that it is an elephant. But for neural networks, it's not as straightforward. And that is good because we want a neural network to be able to make a decision based on this part of the image. The fact that it has this kind of the ears and the head is what is more important, or at least we feel that it is what is more important. So the fact that it has gone down from 95% to 75% is good. This means that it is working as intended. So that also means that these pixels, they affect the decisions more. So let's say it had started off with 100% accuracy or 100% confidence, sorry, that it's an elephant. When you put the gray patch at the bottom right corner, it goes down 95%. There's just a 5% decrease. But when you put it on the face of the elephant itself, there's a 25% decrease. And this is what we want to see of a neural network. Essentially, this means now that your neural network is working as it should be. Now, so this is actually, there's a larger thing at play here. So remember how this neural network is trained. It's trained with this idea of image level labels. So within the elephant image, during training, an elephant image would have been passed through the neural network. You would have just said that the answer is an elephant. That's it. You would have never localized it. You never told a neural network why it is an elephant and said that, okay, this is the head, this is the tusk, and any other thing. But these properties are emergent within a neural network, that it itself has understood that the head, the ears are what makes this image an elephant. And this is a very nice property. Essentially, there's a huge concept called emergent causality, which is part of this. We will not get into it. But the network is trained with image level labels, but it is sensitive to the common visual regions in the image. So that is the case here as well with the elephant. And that is the case with the go-karting as well. And what we can do what we can do with it is basically visualize the heat map. So I have this particular patch here. Let's say I move the patch a little bit to the top left corner here. I'm going to record the probability. I'm going to take this patch, move it a little bit up. I'm going to record the probability, and I'm going to keep doing it. And I'm going to visualize it in terms of this heat map. And this is the kind of heat map I'm going to get. And this is great, right? Because you can see that the place where the lowest probability is in this particular case will be the ones which are masked here. Again, the way this is done is by taking the midpoint of the patch here and saying that the midpoint of the patch is something like 0.75 in this case. It was actually not 0.75. Apparently, it was somewhere close to 0.4 or 40% probability. But we record that number in this particular place. And that exists throughout the heat map within the elephant image. Is it clear how we get this heat map? It's important. I think this is one of the best ways of trying to understand or visualize and understand what is happening within a neural network. We take a patch, we put it on top of the image, we pass it through the network, we just record what the probability is at the midpoint of the patch, move it one over, do the exact same procedure and go through. So at every point, we'll have some heat map of probabilities that can exist for a neural network. Yes. You can use blob or any other shapes. Rectangle is the easiest because convolution filters are also rectangular. So it's the easiest for us to actually code it in. Like if you do a blob, for instance, right? So that means your convolution, this part of your rectangular convolution filters that is on the patch and the other ones that are not, it might get a little bit difficult in terms of calculation. Since your pixel level space is already 224 cross 224, there's so many of these pixels, the resolution is sufficient enough that if you use a rectangular function, it can work to get these kind of things. But yes, if you want to use a blob, it's perfectly possible to use those kind of things as well. Yes. Yeah, this is an issue with this kind of intervention. So if I go back, so intervention by itself is a thing. So mask part of the image before feeding to CNN, check how much predicted probability changes, right? So this idea of intervention is itself a big thing, where any intervention that you put into a neural network or to an image, it has its own uncertainty involved that it adds into it, right? Maybe it's not the thing within the image itself that is making the change. It's actually this mask that is making the change, which is not good, because we want to understand what is happening within the image. The only so there are different papers that go through and see, okay, what this thing has to be. Should it be, sometimes it may not be a gray thing. Sometimes it can be, you can take the average of each channel. So let's say the R channel average is like 64. The B channel is like 127. The G channel is like 162. So 64, 127, 60, 162. Those will be your mask. Like it's the average of the image can be your mask. So that is one way of overcoming it. Um, Again, there's different ways of doing this. There's a lot of research that is done on how to do interventions, and there's not one good way of trying to come up with it. And that's why this is a hot research topic. Like there's a lot of stuff coming out every year, papers that come out every year that do it. So either you can do a gray patch, which is just 128, 128, 128, or you can take the training set. So in ImageNet, for instance, they give you, if you're using PyTorch, they give you what the mean normalization is. You can just use the patches with that mean normalization. Or if you have a different data set, you can take the average of each patch and use it there as well. So there are different ways of trying to do it. Yes. Exactly. So I think that depends on the fine-grained nature of your image. On natural images, at least on ImageNet dataset, you usually have this good-looking images where you have the entire image, you have the centered object. Your elephant or go-kart is always going to be in the middle, and it's going to usually be, let's say, take up 1/3 of the space. So of your image. So if your rectangular box is somewhere between 1/5 to 1/4, that's a perfectly acceptable way of doing it. But let's say you were using some kind of seismic images or biomedical images, where the reason there is a, let's say, a disease classification is because of a very small nodule in the image. So if you take this large set, it doesn't really make sense. So you need to mask it based on a very small thing. Now, the goal of explainability is I can look at the image and I know why it exists. And I now want to know if a neural network knows why this is an elephant, right? So I can decide on the size of this rectangle. Same thing in biomedical as well. I know that this nodule exists, which is a very small 10 cross 10 patch. So now I can make all my patches to be like, let's say 15 cross 15 and go through it. So that's a good question. Yes. So the size of the patch should be dependent on what we as human beings are looking for within the image. If there's no questions, the one problem with this idea of doing it is that it's very expensive. So I think we just had a question about the size of it. We just had a question about what should be the value of it, right? So there are different things that we can try, and we probably should try in order to get what the explanation is going to be. So it can be very, very expensive. Think about something like a 20 cross 20 of this patch that goes through from the top right, to the top left to bottom right in order to get this thing. It takes a lot of time, a lot of computation resources for just one image in order to get this heat map. So this way of saliency via occlusion, even though is probably one of the best methods in order to find the explainability, is not very practical in large scale scenarios, where if it's not just one image and we want to understand for the entire data set if it's working, then we cannot use this method directly because it's very expensive, but it's very faithful as well. That's one good thing. So it does give you a very good idea of how a neural network is working. But we want to correct this aspect of the very expensive part. So this is where we come to the next stage, which is we'll be using some kind of gradients to do it. Now, I want to set that up. Again, the reason we want to move away from saliency via occlusion is not because the method is bad, it's because it's very expensive. We want to find a less expensive approach. So think about what we are doing. Like saliency at the end of the day is feature importance. We're saying that these features or these pixels are as important as my saliency or occlusion of using occlusion is giving me. So it's basically a analysis of feature importance. So in, let's say, a linear layer, the way feature importance is done by a basic W transpose X plus B. If X is your input, a linear function basically has this kind of weight, which adds into your features X, multiplies it by a certain weight. Higher the weight, more is the feature importance of that vector. That is essentially what feature importance is. Like we went through all the saliency stuff, is essentially just feature importance, right? Now we want to generate that kind of saliency based on this feature importance. So we know that a neural network this is how it works. There's a feature 128 224 cross 224 cross 3. Let's just say it's just three elements here. So x11, x12, xi1, xi2, xi3. It gives you at the output yi1 and yi2, which are the two outputs. And there's a lot of non-linear mapping that goes on, a lot of matrix multiplications, a lot of ReLU functions, sigmoid within this. But let's make a very gross approximation of the neural network and say that this entire thing is f theta of x, which is just a simple linear layer. That I'm going to take the entire neural network and say this thing is just a linear layer. And the motivation for this is kind of, you can use this idea of Taylor series and say that the most important one is the first derivative, which is the linear layer. And hence we have this access to this gradient based importance. That is given y, given x, w, and b, the pixel importance is just the gradients dou y cap given by divided by dou x, or the partial derivative of my output given my input is pixel importance. Again, this is based on a very gross approximation that my entire neural network is just a single linear layer. But if you accept that approximation, then the entire feature pixel, the saliency is nothing more than the gradient of the output given the input. So the saliency is approximated by gradients with respect to the input, which can be obtained by backpropagation. We are very familiar with PyTorch, and PyTorch gives us based on a single function, pred.backward or something, you'll be able to get your gradients. And that itself is the feature importance. So let's go through how we actually do this, because this is very important as well. We have this image of a dog, passes through the network, and let's say it's trained on just three classes, dog, cat, and frog, and you have this 0.85 as the logits in your final fully connected layer for this image of a dog. Now I'm going to backward pass. I'm going to compute the gradients in the reverse direction. I'm through the entire network again. So given dog, I'm going to take 0.85. Usually during training, we do this via loss, right? We say that we take some loss of this logit vector, again, something like 001, do some loss and backpropagate it. This time we're not doing the loss, we are directly doing it for the logits. So if I go back, it's do y cap given do x, where y cap is not the loss, it's the logit directly. So we go through, we take 0.85, we backpropagate this logit backwards until the input image. And what you'll notice is this kind of a heat map, saliency map. So hopefully you'll notice that the regions that it is maximally activated, or the highest number, are the ones that are spatially similarly located as the dog in this particular case. The way we visualize it is actually using the max of absolute values. So given RG and B channel, the gradients for RG and B channel, we're just choosing the one which is the max between them for a particular pixel. We're taking the absolute value of that and showing this. And this is the visualization that we get out of it when it is done. Any question on how we are getting this visualization here? So this is a for multiple other images. This is how it looks like. Given the sailboat, you have access to this. The dog, we've already seen it. This tractor and this underwater picture of some fish, I guess. This is where all of them exist essentially. So this is similar to the saliency via occlusion. There we had to do a very large set of computations, very expensive in order to get the saliency. Now we're just doing one backpropagation through the network, just one set of computation in order to get these kind of images. So it's less expensive, and kind of similar, or as maybe, at least by looking at these images, you might think that it's as faithful as the occlusion via saliency. It's not really. We'll come to that in a little bit. It's not as good, but it's less expensive. So if we are trying to do this across an entire data set, this should be the way for us to go and do something. Yes. Yeah, it is right. So any kind of images, it still works. It's just that in medical images, the problem is that it's so small, the region you're looking for. So maybe not this method itself. We'll come to a couple of other methods, guided back propagation, which will be hopefully more important in that case. But the idea is, yes, it is relevant everywhere. So we have just been looking at classification till now as an application because it's the simplest to understand. We're just asking why this decision is made, and these are the regions why this decision was made. But this can happen in different other methods as well. So unsupervised semantic segmentation works as well. So it can work there. Now, the good thing about this kind of explainability, again, this is like why explainability, it can find biases. Like for instance, so you can say that this is a husky. We as humans say it because of the, the face of the dog. But the explanation that a neural network might give might be that it's because of the snow around it. And this is not good. This is if a neural net, and this is the accuracy versus explanation thing we had before, right? Your accuracy might be correct. Yes, it is a husky. A neural network is saying that it's a husky, but it's really not. The neural network doesn't know why it's a husky. It's just by looking at the snow around it, it's saying, okay, this might be the thing. So it uncovers biases within the neural network, and it's very important to try to understand this. Now, we discussed about this kind of vanilla backpropagation, where just backpropagating the gradients, we get some results. Now, it worked well before, but it may not be the best method. And the next few slides are going to discuss, okay, what is a better method of this kind of using gradients in order to show a good explanation. So first, we start off with the vanilla backpropagation. This is exactly what we showed before. Do y cap by 2x is vanilla backpropagation. We'll be calling it this. Given the scat image, this is the region, the gradients. This is how it looks like. Now, the way vanilla backpropagation has worked is essentially we are backpropagating the logits backwards, right? So during forward pass, what happens is, let's take an example of this is our activations. We pass this activations through some kind of nonlinearity. That's RLU is probably the most used activations. So we pass it through it, and anything that is less than zero, anything that is negative becomes zero. Hopefully everybody has used ReLU before. So this is how ReLU essentially works. Now, when we take the gradients from the later layer, what we are doing is not forward propagation, right? It's back propagation. The way vanilla back propagation works is it basically sees that something is 3 and it makes that as 0, because that is essentially how the ReLU is being used. You're using ReLU, or that is essentially how ReLU was used before, because on these red regions, your ReLU had activated itself in order to make it 0. So that is how the vanilla backpropagation has worked, and this is the result that you're going to get. Now, let's make a certain small change to it. So instead of looking at what ReLU was in the activations, if we look at where ReLU is and put it directly on gradients. So let's say 3 still remains a 3, but -2 becomes a 0. Now, if I go back, that was not the case, right? -2 remained a -2 because in the forward propagation stage, your ReLU had nothing to work on here. 1 was positive, so 1 became a 1. -1, on the other hand, had become a 0. So in this case, even though 3 is positive in your gradients, it's going to become a 0 because that is how ReLU has worked in your forward propagation. But a -2 has remained a -2 because in the original forward propagation, nothing happened. Now, in this new concept, so instead of calling it vanilla backpropagation, in deconnet backpropagation, your 3 remains a 3, but your -2 becomes a 0. Right? So instead of looking at where ReLU was before, now we'll be looking at where ReLU is now and using that in order to backward pass and say that this is what you need to use your activations. And when you use that, we say that there is a cleaner saliency map. I don't know if this is the best visualization that we could have chosen to show that it's a cleaner saliency map, because if I go back, there's an argument to be made. One is better than the other or not, but just stick with me for a second. So by doing this kind of a deconnet backpropagation, we can see, or we can show that there's a cleaner backpropagation there. We can take this one step further. we can combine both of these things. So before, in the first case, we used to take -1, saw that in the forward propagation it becomes a 0, and use that in order to make 0 in the vanilla back propagation, right? We keep that. So 3 becomes a 0 because of forward back propagation. -2 becomes a 0 because of decoordinate back propagation. We combine both of them and we call it guided back propagation. So this is another methodology called guided back propagation. And here, I'm sure everybody is going to agree that this is probably more the cleanest image that we get. And in biomedical images, maybe this is a better way of trying to find your saliency. And there's other ways of doing it as well, which we'll cover. But this kind of guided back propagation is giving you, and you can see here that the face of the cat is, I'm not sure if it's as, yeah, I think it is visible within on the screen as well, but only the face of the cat is highlighted here compared to other parts in the image. Any question on how guided back propagation is done? It's a combination of the previous two things. You need to just work out how ReLU is working at the top, and then see the color coded things here and how they relate to each other. You can do that for vanilla back propagation, decoordinate back propagation, and once you understand both of them, the combination of them is going to be guided back propagation. And this would be the result there. Now, the ordering of the slides, it might look bad, but till now we just said guided back propagation, amazing, clean, everything is good. But the very next slide, there are problems with guided back propagation. And this is basically how research works. Somebody comes out with a method. Next day, there's another paper that says, oh no, you're bad. Here's a better method, essentially. So this came out in, well, the tomorrow was an exaggeration, but guided back propagation came out in 2014. In 2018, there was this paper that said that these methods, they're not really class discriminative, that guided back propagation is not discriminative. All it's doing is just reconstructing the image back, or reconstructing the important parts of the image back. So if I ask what the guided back propagation for airliner, so look at this image here. There's like a bus, and there's a plane. So if I ask this neural network why it's an airliner, it gives this kind of an image. If I ask why is it a bus, both of them are equally likely, right? There's plane and there's a bus. So ideally, what I wanted to see in this image for given an airliner, this part of the image is going to be highlighted, while nothing here should be. While for a bus, this part here is highlighted, nothing here should be. That's not the case. We see that both of them are very similar. So in other words, it's not really class discriminative. It worked in ImageNet because the data set is very clean. You have just one class, one image in the middle of the picture. So yes, it's like Instagram quality images, everything works well. But as soon as you have these kind of more realistic images where you have multiple classes, multiple objects within the image, it's really hard for guided back propagation to go through and try to find what the results are. So it's less related to decision making of neural networks, and it just looks at what exists within the image in order to give us the results. So, so these are the two problems. It can be noisy, and it's not class discriminative enough, basically. Between dog and cat, it's very hard for it to go through. Now, the next, okay, this is the summary of these kind of saliency maps based images. One is intervention based, which is based on occlusion, and the other one is the gradient approximations. And all these three methods are essentially these gradient approximations. We'll come to the next one, which kind of combines or hopefully negates some of the problems with guided back propagation. Before we do that, any questions about this particular section? If not, we can go to the next one, which is called GradCam, gradient weighted class activation mapping. So in the first stage, the first 1/3 of the class, we were just visualizing the networks, the activations, the embeddings. And after that, we started looking at gradients and saliency, right? The goal in GradCam is to combine both of these things, both activations as well as gradients. Now, we already know why gradients are important because it gives the importance score, essentially, dou y cap by dou x. Activations are good because it gives us this class discriminative effect. Because if you remember back in maximal activations, the maximal activation number basically gave us different patches within the images. So it has access to different localization that is based on the what exists within the image. So that spatial locality based on the class of the image is reflected in the actions. So these two things, class discriminative nature and preserving spatial information, is what we can get out of activations. And if we combine this with the gradients that we had before, it can be very helpful, can be very effective in trying to understand explainability. And this idea of GradCam essentially goes through and does this. So again, so low level features captured by low layers, high level features captured by higher layers. Essentially, we can think about which layer we can use in order to get this as well. So gradients, we are just limited to one thing, right? The first layer. We take the entire neural network, we make a very bad approximation that it's just a linear layer, back propagated to the input, and we show what the results look like. But by using activations, we can actually say that, okay, we can use this layer, the last final fully connected layer, or the last convolution layer, or the first convolution layer. Anything we want, we can use that in order to make, or in order to show these explanations. And it depends on what we want. If we want some kind of class discriminative explanations, we need to go towards the higher layers. If we want a feature-based thing, if I want to see where the edges are, I can look at the beginning few layers, essentially. We can see where the perturbation can happen. So let's start with trying to understand the method of GradCam itself, and we'll also see what the results in GradCam look like in a little bit. So given a CNN, I have the cat dog image that we have been looking at. We pass it through that image. We get some kind of rectified convolution feature maps, just straightforward. Any task-specific network, let's say a AlexNet, VGG16, anything works in this case. We pass it through this neural network. This part of the network, we can think of it as the convolution layers, different rectified convolution feature maps. And then the next part, you can think of it as the fully connected layer thing. So that's how we are dividing it, or at least visualizing the different parts here. And at the end of the day, we are going to get some kind of image classification. So this image is going to be classified as a boxer. So the dog is the breed of the dog is boxer, and that is how it's going to be classified as. Now, let's say we want to have an explanation out of this. What we do is we perturb neuron activations in the last convolution layer and see how it affects the decision. In other words, till now we were looking at how the gradients were working in the input layer, but now we'll be looking at how the gradients are in the last convolution layer. I think that is very important here. We're not doing it, we're not making that approximation from the input to the output. We're making approximations in between. So in this case, to the last convolution layer. So gradient-based backpropagation to obtain activation importance. Now, it's not the feature map importance or the pixel importance, but rather the activation importance that is going to be important for us. So let's start with backpropagating the Cth class. So in terms of arrows, by the way, you can stop me anytime if you have any questions on how the methodology is done. It's a little bit complicated, and your homeworks are, one of your homeworks is going to be based on actually coding this. So probably in your best interest that you understand this completely. So you have an image, you pass it through the neural network. The black arrows are essentially going to show you the forward propagation. So you pass an image through the network, do everything that is normally done, and you get boxer class out of it. Now, given that it's a boxer, or knowing that the network has predicted a boxer, you want to know why it predicted a boxer. So you backpropagate the boxer class. Again, you're not backpropagating the loss function, you're backpropagating the logic directly. This is what we did in gradient vanilla backpropagation as well. So we backpropagate the Cth class backward through the neural network. So with respect to feature maps, so again, before we used to have dou y by dou x. That means it's with respect to the input. Now it is respect to the feature maps. So it's going to be dou y by dou capital A, let's say, because it's with respect to the activations in this particular case. So this is basically how it's going to look. Dou yc by dou ak. Let me just go through and discuss what the exact nomenclature here is. Yc is your boxer, your Cth class in this particular case. Ak is your activation channel. So let's say your final last convolution layer has 64 channels. So AK is, and you're interested in the fifth channel. So fifth channel in your last convolution layer is what AK is going to be when K is equal to 5. So what we do is we backpropagate to the last convolution layer. In this case, I don't know which one it's going to be, but think of whatever number you want. The last convolution layer, we're going to do something called global average pooling. So let's say I have the last convolution layer has a dimensionality of 64 cross 3 cross 7 cross 7. In that case, what I'm going to do is I'm going to average pool the 7 cross 7. So I'm going to average pool whatever the width and height of this activation map is. And I'm just going to literally 7 cross 7. I'm just going to add everything. I'm going to take it as a vector. I'm going to add everything. That and of course divided by 1 by z, which is the average, in this case 1 by 49. So essentially I have access to this thing called alpha kc, which is my importance score. So the addition of all kernels of your gradient map is going to be my importance score. Again, the kernel map is the backpropagation. Before, we just used to visualize the backpropagation. Now we are not doing that. We are using that as an importance score. We are taking that gradients and we are just adding it and calling it importance score, right? So dou yc by dou akij is essentially my gradient map that I have now added together or average pooled in order to get this alpha kc, which is an importance score. Given that alpha kc, I'm going to multiply it against the channel. So if I had 64 channels in the beginning, now I have 64 numbers of gradients, and I'm going to multiply those numbers with every single activation in that particular channel. Think of it as just a scaling. And after that, I'm going to just collapse all channels. So I used to have 64 channels, each of with whatever you want, 7 cross 7 as the activations. When I backpropagate it, I get the same exact size of gradients as well. I'm gonna take an addition of all the gradients and call it an importance score and multiply that with the channels, with the numbers within the channels to get this linear combination here. It's alpha kc multiplied by ak. And once that is done, I am going to collapse all channels by just adding. Again, very simple. I'm just adding through all channels to see what the map is, and I'll pass it through ReLU. That is, if something is negative, I'll just make it positive. I'll just make that 0 because I'm not interested in the negative activations. I'm just interested in the positive things that contribute towards a score. And once I do that, this is the GradCam that we get out of it. So given a boxer, this is essentially the region of the boxer or region within the image that gives me that that shows me that the image is that of boxer. Any questions here? The math might appear complicated, but it's not. Once you start coding it, there is a starter code available, of course. So once you start coding it, you'll see that all of them are kind of straightforward. Once you have the gradients, you just sum up the gradients and you multiply it against the channels, add all channels together. That's it. And of course, and then pass it through ReLU. But once you do that, you get this kind of a feature map. You just feature map, you just upsample it. That's all at the end of the day you would have to do. Sample it to 224 cross 224, and you can put it on top of the image and you have this kind of a heat map. So this is actually a combination of multiple methods. So this is basically just gradients via backpropagation, right? This is the first thing that we saw. We're not doing any guided backpropagation. You can do it actually. There's something called guided GradCam, but not important for now. So you can take the vanilla backpropagation itself instead of backpropagating to the first layer or the input image. You're just backpropagating until some kind of a middle feature, and you're doing this kind of global average pooling on top of it. That's it. So it's just a combination of multiple methods that we have discussed till now. Now, the good thing about this is that it can generalize to different tasks. Again, we just looked at image classification, but it can do for image captioning as well, and for visual question answering. So the next couple slides will actually talk about what they are. So for classification, this is essentially what the results are going to look like. So if for this given input image, guided backpropagation, again, it's not class discriminative. It just basically gives you all the important parts of the image. So you have the bat as well as the torch. So if you want to look at the torch, GradCam is actually going to just highlight the torch portion of the image compared to guided backpropagation, which shows everything. Same thing in all the other ones as well. Umbrella is, you have access to the entire thing, but GradCam just gives you the umbrella and so on. So one of the better methods and one of the simplest explanation methods out there is GradCam. So this should be, if you're looking at these kind of methods in order to explain your neural network, this should be your first choice. GradCam probably should be your first choice. And there are tons of open source codes out there for actually doing it. So you should be able to go through and do it for project or anything. You should be able to use GradCam. So this is visual explanations for classification. Now, another application is image captioning. So given this image here, if it captions, given a neural network, it captions says it's a bathroom with a toilet and a sink. Now, this is the output of why the neural network says it's a bathroom with a toilet and a sink. Now, if I give this image as the input, the neural network is going to spit out a horse is standing in a field with a fence in the background. That essentially is image captioning. The application is basically given an image, a neural network gives you a certain caption. GradCam shows you why this particular decision was made, or why this horse is standing in the field was spit out, essentially. Again, another good thing with GradCam is this idea that failure modes are done. So if your method is not working well, for instance, and you know that this particular image is always giving the wrong answer, you can actually see GradCam why it is happening. So given a volcano, so given this image here of a pineapple, it actually predicts it's a patio rather than a pineapple. And it kind of makes sense, right? It is a, you can think of this as a patio as well. Like, yes, there is a pineapple in the middle, but there's other regions of the image, and the neural network is making a decision based on the other regions of the image. So you can analyze why your neural network is not working well by using these kind of explanatory setups, which is GradCam. So that essentially brings us to the end of this lecture. Next time, we'll actually go back and try to understand what an explanation is. Like, what we saw was all different methods, but all of them were answering just a specific kind of a question. So next time, we'll just expand this definition a little bit more and discuss what other explainability is, and then see how we can evaluate. Till now, our evaluation of explanation was only, okay, I'm looking at it. This looks nice to me, but I am different from you. It's very subjective looking at it, this human being way of evaluating it. So there are different ways of objectively evaluating explanations. And that is also something that we'll do next week. Before that, any questions before we finish for today? Yes. Mm-hmm. Yeah. And yeah, so there's a new way of, so till now we have studied CNNs, right? There's a new whole different breed of neural networks these days called transformers. I don't know if you've heard of this. The GPT and all these things are based on this idea of what transformers are, where you have attention is the one that guides the decision-making process. So now we are analyzing explanations and saying this is why it's not working, right? You can now take this analysis or this attention, put it within the neural network, retrain it in order to get what the result is going to be. So it's think of it as a bootstrapping mechanism. Till now, we have thought of explanation as something that justifies a decision, but now we can start using it as a way in order to make a decision as well. So you can use this as an attention mechanism and say that, yes, this is a patio if you look at all the other sides, but I want you to look at only this middle portion here. That is the most salient part of the image that you need to focus on in order to make a decision process. So instead of a retroactive way of using it, we'll prospectively start using explanations as well. So let's say different kind of architectures, or there's different ways of using it in that way. Yeah. Any other questions? All right, if not, then I think this is the end of today's lecture. Thank you. I'll stop.